Hello, and welcome back. I am Sam, your lead tutor. Today, we are going to learn how to be a detective when things go wrong. We are tackling K65, Principles of Failure Modes in Protocols. This knowledge point is about understanding why a protocol might hang, the effect of data communication errors, and how to fix them. Think of a network connection as a conversation between two people. Sometimes, one person stops talking, a hang. Sometimes, the phone line is crackly, errors. As a network engineer, your job is not just to see that the conversation stopped, but to understand why. Was it the phone line? Did one person fall asleep? Understanding these failure modes allows you to optimize the network and prevent future silence. This knowledge point is about understanding why a protocol might hang, the effect of data communication errors, and how to fix them. Think of a network connection as a conversation between two people. Sometimes, one person stops talking, a hang. Sometimes, the phone line is crackly, errors. First, the hang. This is when a system waits for a response that never comes. It's like saying, hello, into a dead phone line. The protocol eventually times out. Second, the error. The data arrives, but it is corrupted. It's like receiving a letter that has been soaked in water and is unreadable. Third, the storm. This is congestion. The protocol is working, but the network is so busy that packets are being dropped or delayed so much they become useless. Your role is to look at the symptoms, slow application, disconnects, error messages, and map them back to one of these three root causes. Let's look at the first failure mode, the protocol hang. This happens when a protocol, like TCP, sends a packet and expects an acknowledgement. It sets a timer. If that timer hits 0 before the reply comes, the protocol times out. Why does this happen? Usually, it's packet loss, the request got lost on the way, or the reply got lost coming back. Or, the server itself has crashed and can't reply. The impact on the user is frustration, the spinning wheel of death. To fix this, you need to determine if the path is broken, using ping or traceroute, or if the destination is dead. The second failure mode is data errors. This is corruption. Imagine sending a digital file. On the wire, a 0 might get flipped to a 1 because of electrical interference or a bad cable. Protocols use a mechanism called a checksum or CRC. The sender does a math calculation on the data and sends the result. The receiver does the same math. If the results don't match, the packet is corrupted and instantly dropped. For TCP, this means the sender has to send it again, which slows everything down. For UDP, like video, you just see a glitch on the screen. If you see high CRC errors on a switch port, it's usually a physical layer problem. Go change the cable. The third mode is related to how protocols handle speed. This is TCP windowing. TCP tries to send data as fast as possible, but if the network is congested and packets start dropping, TCP assumes it is being too aggressive. It reacts by cutting its transmission speed in half instantly. It then slowly ramps back up until it hits the limit again. This creates a sawtooth pattern on a graph. The user experiences inconsistent speeds. This is a failure of flow control. To fix this, you need to manage the congestion using quality of service, COS, or buy more bandwidth. Let's look at a real-world scenario. A user complains that large file transfers to the backup server keep failing right at the end, around 90%. You investigate. You don't just look at the server, you look at the network path. You check the switch interface statistics and see a high number of FCS errors or frame check sequence errors. Diagnosis. The protocol is failing due to data corruption. A faulty fiber cable is flipping bits. TCP is trying to retransmit the corrupted parts, but eventually, it hits its limit and resets the connection. The resolution was simple: swap the fiber patch lead. The errors stopped, and the protocol could finish its job. K65 isn't just about fixing breaks, it's about optimization. You can tune protocols to handle failure better. For example, in OSPF, you can adjust the hello timers. By default, it might take 40 seconds to realize a router is dead. You can tune this down to 1 second for a near-instant failover. For TCP, on long-distance links, you can increase the window size so the protocol sends more data before waiting for an acknowledgement. This overcomes the latency of the distance. Your goal is to tune these settings so the network is resilient and recovers from failure before the user even notices. For your portfolio, K65 requires you to show deep analysis. Use the STAR method. Situation: the critical ERP application was randomly disconnecting users. Task: I needed to find the root cause. Action: I performed a packet capture using Wireshark. I analyzed the protocol headers and identified a pattern of TCP retransmissions followed by a TCP reset. This pointed to packet loss. I traced the connection and found a duplex mismatch on a switch port. Result: I fixed the duplex setting, and the errors vanished. Reflection: I learned that looking at the protocol level, layer 4, is the only way to reveal certain hidden physical faults, layer 1. If you are doing your major project, apply K65 in your testing and validation section. Don't just test that it works, test that it fails correctly. Write a test case. I physically disconnected the primary link to test OSPF failover. Then provide the evidence. The logs show the protocol detected the failure and reconverged on the backup link in 2 seconds. Mention any optimization. I tuned the timers to ensure this failover happened fast enough not to drop voice calls. This proves you built a robust, professional system. To conclude, remember that protocols don't just break randomly. They fail for specific reasons: timeouts, corruption, or congestion. Your tools, ping, traceroute, Wireshark, are your stethoscope. Don't just reboot the router and hope for the best. Diagnose the failure mode. If you can understand why the protocol hung or why the data was corrupted, you can fix the root cause and build a better network. I challenge you to log into a switch today and run a command to show interface errors. Look for CRC or FCS errors. If you find them, you found a patient that needs your help. Thank you for your focus, and I will see you in the next session. Thank you so much for joining me today. I hope you now feel more confident in mastering this topic. If you found value in this session, I have a small favor to ask. Please hit that subscribe button, give this video a like, and follow our channel. It really means a lot to me and helps the algorithm show these lessons to other apprentices, just like you, who need support. Don't forget, you can download today's slides and the full transcript at www.mentorinai.com EPA Hub. While you are there, check out our mock interview and portfolio review services to make sure you are fully ready for your EPA. See you in the next video. Keep learning.